Okay, in exponential growth, we have another really common base, which is e. And e is an irrational number. It's kind of like pi in that sense that it's irrational. It's approximately equal to 2.71828182. I can't read numbers. If you go on your calculator, you will find e right above your ln button. And we're going to be getting to ln later on. So if you clear this and you type in second ln, you get e, and it will automatically want you to have an exponent. If you put in the exponent of 1, there's that same number written on the calculator. Okay, so it is just a number in between 3 or 2 and 3. So when we graph it, it's going to be similar to graphing 3 to the x. It's going to be a little smaller, and it's going to be a little bit larger than the 2 to the x that we did before. So we use it a lot for exponential growth. And if you want to use your calculator to graph it, you can go y equals, and I guess I might as well clear. Actually, you know what I'm going to do? I'm going to make that one 3 to the x, and then you can kind of see how this one compares, because especially I have a color screen so you can see the different ones. So if I want to graph that, I'm going to go second ln e to the x this time, and then we'll graph it. And we're seeing a very similar shape. So actually that's the 2 to the x, and a little bit bigger, the next one coming up. Well, no, we did 3 to the x. I did the order wrong. So there's 3 to the x. And then in between, but closer to 3, is going to be e to the x. In fact, it's almost tracing 3 to the x, right? Because 2.7, that's pretty close to 3. If I wanted to create a table of values for that, does everybody know how to get to the table on their calculator? Second graph, I hope so by now. Okay, and now I have 3 different tables, because here's all my x's, and I have y1, y2, and then over here, that's e to the x. So I went really far with my negative exponents, but essentially we see this exact same picture arising. Okay, so if I wanted to graph, okay, what's our y-intercept? All of them have the same y-intercept, 0, 1. You got some pretty small numbers for your negative exponents. So here, maybe you're going to see that asymptote happening. And then to the power of 1 is going to be 2.71 rounded off. So there's the power of 1, 2.71. Power of 2, 7.3 approximately. 7.3 is like around here. Okay, and so there's our graph e to the x. Now we're going to use the value of e in this exponential growth word problem, thinking about population growth. So suppose the population of a city is currently 24,000. The population is expected to have continuous growth rate of 5% per year. So this is where you see the 5% as the decimal as part of your exponent. The population growth equation is P of t equals 24,000. Now, we were talking about in the beginning, this is our starting value. This is our initial amount. In the past, we didn't see that with the other graphs. We were using elementary exponential functions, but now this one has an initial starting value. So you see the initial starting value, and you will see this in Connect Math denoted usually n sub 0. N sub 0 is the initial amount. Okay, and then we see the 5% growth rate as part of the exponent over t years. Evaluate P of 0. Interpret your results in a complete sentence. So P of 0 means what? I'm going to plug in 0 where? Yes, for t. So I have e to the 0.05 times 0. Well, what's anything to the 0 power, you guys? Yeah, so this whole thing is 0 power. E to the 0 power is actually 1. So what's 24,000 times 1? 24,000. And if you want, you can plug that in on your calculator just to make sure. I'm a fan of checking, you know that. So, oops, that's the wrong quit. All right, so if I plug that in, 24,000 times e to the 0 power, and if you want, you can even put the decimal times 0. Okay, you get 24,000. Why did I get 24,000 if p is 0? What does p of 0 mean? That, yes, that's the y-intercept. Exactly. The population starts at year 0 at 24,000. And maybe people. I mean, you probably have a better wording of that. Population starts at year 0 at 24,000 people. And that's also, I love that you said that's the y-intercept. Because 0, 24,000 is where we're starting from. And of course, you know, whenever we started calculating this, you know. Okay, find the population after 5 years. Answer in a complete sentence. So we would be doing P of 5. We're going to plug in, where are we going to plug in the 5? Yes, 0.05 times 5. And I will use my calculator to approximate. Now, what should we, if I do get a decimal here, which is very likely, what should I round? How should I round population? Times 5. Does everybody see how I entered that? Is that the same answer you got on your calculator? And for population, we'll round to whole numbers because we don't want fractions of people. So, and they didn't say what year this started. So after 5 years, the population is 30,817, approximately, is about. Let's do that. Okay. Any questions on that? Oh, I remember something else I want to say about that. Okay, so let's say I had, and this is where we're going with this next. This is not on the paper, so I'm adding a little bit of paper. What if I said, when will the population double? Or like after how many years, right? That would mean I wanted to solve when P of t, what's double the population? 48,000. Okay, so let's say I was going to try and solve that equation. I would say I would set the equation 24,000 e to the 0.05 t. I would set that to 48,000. And then what would I do to solve? I'm trying to get t by itself. What should I do first, do you think, to solve? Well, this is just multiplied, so could I divide both sides by 24,000? Does that make sense as an inverse operation? I'm kind of getting closer to getting my variable by itself. How many times does 24,000 go into 48,000? 2 times. Oh, there's where you get the idea of double. Okay, I'm giving you some hints because this is kind of the wording they use on Connect Math. Is if they don't even tell you what the initial population is, but they want to know when it doubles, you could set it, you know, if you didn't even know what n sub 0 was, you're setting your exponential equation to 2. But now we know inverse operations, addition, subtraction, multiplication and division, squaring and square roots. The problem I have right now is I don't know how to get that variable out of the exponent. Do you guys know how? Well, it's because we haven't learned it yet. We need another inverse operation. We need a way to get the variable out of the exponent. And that's why we're learning about logarithms. That's coming up next, okay? But I did want to show you that if you did want to solve this problem using your graphing calculator, you could go back to your table of values and you could keep scrolling. Well, once you put, let's say you put in your equation, okay? I'm going to clear out this, clear out this, clear out this, clear out everything, clear it all. Okay, I'm going to put in my equation, 24,000 e to the 0.05, and I have to use x, I can't use t, okay, because your calculator only understands this independent variable x. Now, if I graph that, first of all, I pushed graph, and I'm not seeing anything on my screen whatsoever. Why do you guys think that is that I wouldn't see anything on the screen? Oh, the y-intercept is 24,000. So it's not even going to start here. I would have to change my window, and I would need to include at least 24,000 on my y-axis. So the maximum, let's actually go up to 100,000 on our maximum, and then press graph. And you see this, there's our y-intercept. That's 24,000. Now, eventually, we probably make it up to 48,000, right? So another way we could do this, if I say y, what would the line y equals just 48,000 look like? Y equals 48,000. What kind of line is that? A horizontal line, right? So if I press graph, y equals 48,000, eventually these two graphs are going to touch. Well, I know it's going to happen beyond 10 years. Can you tell why I would have to go beyond 10? Because you see this is our exponential function reaching out and touching that line. So let's go back to our window and we'll set our x maximum to 50. That's 50 years of exponential growth, okay? Eventually, they're crossing. So that point right there, if I can find that point of intersection, I will know when the population has doubled. I will know my x value. How would I find that point of intersection? Any ideas? Second, calculate. Is there a button on here that gives me the intersection? Intersect. Is this my first line? Yes. Is that my second line? Yes. Is that a guess? Yes. So you push enter 3 times. So x equals 13.86. Let's round it off to 13.86. So t is approximately 13.86. And if we were going to plug that number in, or if I went back to my table and scroll down to 13, we should see at 13, let's get there, between 13 and 14, look at that. 14, my population is 48,330. So that's just one way. We haven't learned about logarithms yet, but you could still use your calculator to help you solve. Does that make kind of sense how I did that? Okay. Any questions?